Can everyone hear me? Yeah. Yes? Okay. Okay. Thanks very much for that introduction. I'm very glad to be here tonight opening up this symposium. But when I received the invitation to do so, I tried to think about what I could say to you all that would really be useful to you. I'm not an expert on the arts, as you know. I'm not an artist. And nor am I an activist. My experience is really fits very squarely in the form of writing that we call journalism. And I spent almost 15 years writing for the New York Times, where to maintain at least the semblance of objectivity, we weren't supposed to engage in any sort of political activity. Some of my colleagues weren't even registered with the party, just to avoid any semblance of any appearance of favoring one side or the other. We weren't supposed to march. One of my colleagues got in a lot of trouble for marching. So we were really supposed to avoid political action. So what's my connection here to a symposium on art, action, and climate change? Well, basically, I think I'm here because, like I assume most of the people in this room tonight, I am very concerned about the lack of action in this country, frustrated, even frantic, to be honest. And I'm also concerned about what I can do to move this issue forward. And I'm hoping really to start a dialogue tonight and learn from all of you as well. So the business of journalists is, of course, to represent the world. This is our point, this is what we're up to, and it's a point of contact with art and also with science, which really forms the basis of what we know about the ways in which we humans are currently changing the planet. We all draw upon different methods of representation and have different goals, but when it comes to climate change, we're really all sort of thrown together. Journalists have to rely on the scientists, and artists, unless they have a great deal of time on their hands, probably have to rely on journalists. And so I've divided my talk tonight basically into three parts, or if you prefer, stages. I'm going to start by talking about how scientists have tried to represent climate change. Then I'm going to talk about journalists and how we've tried to represent the work of scientists. And then I'm going to talk to the extent that I can about art and what it has to offer. So first to the scientists. As you all know, science is the realm of numbers, and numbers are absolutely essential to understanding global warming. And the privileged form of representation in the sciences is charts and graphs. And any of you who have looked into the science of climate change, and I suspect that that's just about everyone here tonight, is familiar with a lot of these. And I'm just going to show you a few of them because they are, I think, if you know how to look at them, very powerful. They're also very elegant. They convey a lot of information very economically. From a design perspective, I'm sure, from a design perspective, you really actually have to admire them, I think. Though I'm sure that there are graphic designers here tonight who could improve on some of them. And if you talk to scientists, they will say, and I don't want to put words in their mouths, and there are some scientists here tonight who can correct me, but some scientists have said to me, this is really all you need to know. If you have the 4 or 5 graphs that I'm about to show you, charts, you really have the whole story. And to a certain extent, they're right. So this is the first chart, a very famous one. I'm sure pretty much everyone has seen it. It's called the killing curve. Here we're looking at levels of CO2 in the atmosphere over time. They've been measured pretty much continuously since 1958 at an observatory on the island of Hawaii, on Mauna Loa, so about 11,000 feet up the National Weather Service Observatory there. And what you're seeing with that zigzag signal is a seasonal signal, because when the trees of the northern hemisphere, of the vegetation in the northern hemisphere is growing, it's taking up CO2 for photosynthesis, and atmospheric CO2 levels actually drop. So during our summer. And then in the winter, when vegetation and trees are dormant, atmospheric CO2 rises. So that's the sawtooth that you're seeing. But on top of that, you see that very, very clear upward trend. This is a pretty up-to-date chart. We're now just over 390 parts per million. So this is starting, as I said, in 1958, pretty much 50 years of continuous data there. So here we have also a very famous graph. I'm sure many of you have seen this too. This is a representation of a very, very fascinating thing. You may have read recently that Russian scientists had broken through to a lake in Antarctica, Lake Vostok, which has been sealed off from the atmosphere for millions of years. And there's been actually a lot of debate about whether they should have done that. We're going to leave that issue aside for today. But to get to Lake Vostok, they drilled a core. The purpose of that core was to look at climate data. So Lake Vostok sits under several thousand feet of ice. And Vostok is the coldest place in the world, or the coldest place that's been recorded. They've recorded temperatures there of minus 128 degrees. So this was a really brutal project. It took many years. They drilled this ice core. And what ice cores do that are quite fascinating is all an ice sheet is, the Antarctic ice sheet, the Greenland ice sheet, it's just layers of snow that have built up over time. And if you drill a core, you literally take these cylinders of ice out of the ice, and you can basically go all the way through the ice core. That's what they did, all the way through the ice sheet, excuse me, so many thousands of feet of ice. And if you look through them, if you're very talented, clever, you can extract two kinds of data from this. You can extract temperature data, what was the temperature like in Antarctica when that particular layer was formed, and also you're getting actual bubbles of the past atmosphere. So you're getting temperature data and you're getting atmospheric composition data. And what we see there is the temperature in red and the CO2 concentration in blue. And you see how over the last 400,000 years, okay, so we're going backwards in time to your left, we're about 400,000 years ago, and then we're going forward to today. We're seeing 4 glacial cycles there, okay? And you see how CO2 levels and temperature rose more or less in tandem over the last 400,000 years. So that was an extremely important graph when they first correlated that those data. So this is another graph, not quite so well known, and in fact, it probably could use some design work, to be honest. Here we are looking at CO2 levels over the last 45 million years, and now we are looking in a different way, going backwards in time is going to the right. So those are millions of years ago. So back into the Eocene. And we can't get ice core data going back that far. We just don't have any ice on the planet that's old enough. So we use, scientists use proxy data, pretty complicated science. I'm not going to go into it. But and the reason that there's that big, orange span there, those are the error bars. But what that's showing you is that carbon dioxide in the atmosphere has been below 500 parts per million, basically since the beginning of the Miocene. So people now feel, there's pretty good reason to believe, that CO2 levels have not been as high as they are very, very rapidly approaching for the last 50 or 20 million years. Okay, so that's a pretty important piece of data too. So the next thing I'm going to show you is a very recent creation from NASA. Some of you might have seen it on the internet. It's a video. This is the first time I've ever tried to show a video, so I hope it works. It's going to show you just what has happened to temperatures over the last 130 years or so. So since we've had recorded temperature data, we're not going on any kind of proxy, we're going on recorded temperature data. And the key to this is the more yellow or red you see, the more temperatures have gone up. Okay, so let's see if we can do this. Okay, we're starting in 1884. So this is a pretty dramatic representation, I think, of where we are. You can find that maybe on YouTube. It's many hundreds of thousands of hits. This is not a graph, it's a map, but it's done with satellite data. We can actually take those shots. We're just looking down at the Arctic ice cap. as if we were standing there, as if we were hovering over the North Pole there. That's what the Arctic ice cap used to look like. That's what it looked like after 2007, a year of record melt. And that's basically what it looked like after the melt season this past year. The Arctic ice cap expands in winter when it's dark up at the poles, and it shrinks in the summer when there's 24-hour sunlight. So we see that the Arctic ice cap is really melting away. It's on track to melt away entirely within the next few decades, amazingly enough. So we will wake up one day, those of us, the students in this room who are still around, and find one summer day that the North Pole itself is ice-free in the summertime. So here's the very last chart I'm going to show you from this perspective. This one is not at all elegant, but it's the best I can find. These are scenarios, emission scenarios. Every one of those lines represents a different emission scenario. And then on the y-axis there, we're getting, okay, what temperature increase do we get out at the end if we continue on the path, these different paths? And the thing that's important to realize here is we are now tracking that very highest path, that A1F1 scenario. In fact, we may have exceeded it even. So we're on track for, if we keep on our merry way, let's say at 4 degrees Celsius temperature increase by the end of the century. So that's pretty extraordinary. Okay, so all of these are representations. I hope I've convinced you that they do tell a story about the past and the present and the future. And it's quite a scary story. It's a story a little bit like Oedipus. There's a prophecy. Science tells us if we put more CO2 into the atmosphere, temperatures will go up. And that prophecy is now in the process of coming true. And we've been warned about what will happen if we continue to spew greenhouse gases into the air. It's in those graphs and it's in those scenarios. And even as one warning after another has been borne out, we've seen rising global temperatures, we've seen the Arctic sea ice shrink away, we ignore them. And as an Oedipus, the consequences are likely to be quite severe. And I think for longtime scientists who don't tend to see their work in the same vein as Sophocles, operated under the assumption that this wasn't a tragic narrative. In fact, it was a happy one. And if we just gave people the data, they would respond appropriately. And this is what had happened with ozone. This was a model that many scientists used. The chemistry behind ozone-depleting chemicals was discovered only in the 1970s. And it was discovered pretty much by accident. A couple of scientists got interested in the question of what would happen to certain chemicals in the upper atmosphere. And when they did the calculations, they went, whoa, these chemicals, and this is mainly chlorofluorocarbons, are really, really dangerous. They are stable at ground level, but up in the upper atmosphere, they will destroy the ozone layer, which, as it happens, is crucial to life on Earth because it shields us from ultraviolet radiation. So Sherry Rowland, who shared a Nobel Prize for his research on the subject, came home one night and told his wife, and this is a very famous story, the work is going well, but it looks like it might be the end of the world. And then about a decade later, just as predicted, instruments began to pick up what we refer to colloquially, and sustainably, as the ozone hole over Antarctica. And the instruments we would have known about this earlier, but NASA had programmed its machinery to discard as erroneous readings that were too low. So they basically had programmed out the problem. And when they finally woke up to this, the usual sort of prevaricating and foot dragging ensued, not from NASA, but from the political establishment. So those of us who are old enough to remember the Reagan administration, you recall that the administration originally took the position that people should just wear hats. This is absolutely true. No problem, we're just going to wear hats. Donald Odell was Reagan's Interior Secretary, and he said, and this is another famous quote, people who don't stand out in the sun, it doesn't affect them. But even in the Reagan administration, sanity eventually prevailed. And in 1987, the US and pretty much every other country on the And that treaty established the principle of common but differentiated responsibilities. And what that basically meant is that the developed world, so-called developed world, would go first, the industrialized world, and then the developing world would follow. And there would be a phase-in of the phase-out. How's that? And to somewhat oversimplify, that basically worked, and basically CFCs are being phased out, though owing to the law of unintended consequences, some of the substitutes that we now use for CFCs, which are known as HFCs, are turning out to be a very large problem in and of themselves. They turn out to be very powerful greenhouse gases, and they really also need to be phased out. But basically, this treaty did what it was supposed to do, and although the ozone hole is still a very serious problem in some parts of the world was saved from really cataclysmic damage. And Paul Crutzen, who's another chemist who shared the Nobel Prize for his work on ozone-depleting chemicals, has pointed out that if CFCs had behaved just slightly differently in the upper atmosphere, or if bromine had been used instead of fluorine to make these chemicals, then by the time anyone even thought to look into the matter, the ozone hole would have been shot, basically. This is a quote from Paul Crutzen, more by luck than by wisdom, this catastrophic situation did not develop. He's written. And you might have thought that given that rather close brush with planetary catastrophe, definitely too close for comfort, people would have been rather careful, also rather chastened. And many scientists, if you speak to scientists who were working in the early days of climate change research, that's what they sort of thought, that this would follow the same path as long as they were warned about the problem and the world would come together and solve it. But unfortunately, all of the scientific warnings that have been issued about climate change, they've now been issued by virtually every major scientific body in the world. They sort of have started to pile up like dead leaves. And they have essentially been ignored. Their import, at least, has been ignored. So this is where journalists like me come in. If people had simply paid attention to the scientists, to be honest, I would probably be doing something different right now, like covering the Republican primary campaign, another depressing possibility. But around 10 years ago, or 12 years ago, I guess, by now, I started to wonder about exactly this question. Why wasn't anybody paying attention? Were they justified in not paying attention? You know, was this something that really wasn't that serious, or really wasn't resolved? Or was everyone just sort of sleepwalking toward disaster? And at that point, I had just gone to work for the New Yorker, and it seemed like if there was a magazine that had the resources to try to look at this question, and the audience that would be interested in the answer to this question, it was the New Yorker. So I began just, what reporters do. I just sort of started calling around to scientists at the beginning, trying to figure out what was going on. And pretty soon, it became clear that, in fact, people were just sleepwalking toward disaster. The science of climate change is not that hard, as you all know, and it's not really debatable unless you're prepared to debate the basic laws of physics. So I thought, that I really had to try to figure out a way to tell this story. A very important, extraordinarily important story, truly perhaps the most important story of our time. It just didn't seem like it was really getting through to people. And to be frank, I sort of soon learned why that was, why the story wasn't really being told. It turns out to be really tough. I mean, in the sense of self-pitying now that I say it out loud, that it's a very tough story to tell. Because global warming isn't a good narrative. It just doesn't have a good narrative guts to it. The best evidence of global warming comes from average global temperatures. And pretty much by definition, right, nobody actually experiences average global temperatures. So you have this problem that climate change is everywhere and everywhere at once. It lacks particularity, and a narrative is, of course, all about particularity, the experiences of a particular person or people at a particular time in a particular place. narrative demands detail and texture and nuance. And also, another very serious problem for narrative is there's a very significant time lag to global warming. This is, in fact, a really big part of the problem. Climate change is always further along than it appears. What we are doing by throwing CO2, greenhouse gases, but mainly CO2 out into the air is we are throwing the Earth out of energy balance with space. The Earth is actually absorbing more energy than it is radiating back out to space. And that's sort of counterintuitive. The Earth is always radiating energy out. It is in the form of heat, and we're trapping some of that heat. And in order for the Earth to return to equilibrium with space, which according to the laws of physics it must do, you have to basically heat up the whole planet. And that is what we're doing. You have to heat up the oceans, you have to melt a lot of ice. Eventually you will reach a new equilibrium. But it takes 30 or 40 years basically for the greenhouse gases that are up there to, as it were, work their way through this system. So the effects that we're feeling now are the result of, once again, just sort of integrated over time, but in a very rough sense, they're the result of greenhouse gases that were put up into the atmosphere decades ago, and what we're putting up today will affect our kids 30 or 40 years from now. But by the time you feel those effects, it will be too late to do anything about it, because CO2 is a very long-lived gas. For all intents and purposes, carbon dioxide, like herpes, as they say, is forever. So once again, narrative is about the here and now, and it's very hard to write a narrative about a possible future, unless you're a science fiction writer, in which case you can write about the future as if it's the present, which is, or at least can be, in terms of best science fiction art. So I'm going to get to that in a little while. So anyway, to make a long story, not that long, I found it really hard to get the kind of detail that you need for a nonfiction narrative. And I kept getting pushed up to the Arctic, which is really where climate change is still most apparent. But I was still having trouble finding what we in the journalism business call a hook. And then finally one day, someone told me about this tiny island that was disappearing. And this is the island of Shishmaref. So I flew out to Alaska pretty much as soon as I could. First to Nome. You have to fly to Nome. I don't know if any of you have ever been to Nome, but it's kind of an extraordinary place. It's like it's sort of like a stage set from the Wild West. And from there, you can only take like the 6-seater bush plane to Shishmaref. And I went up. There were a couple of other passengers and a woman who was taking a load of reindeer meat for the sled dogs up there. So Shishmaref, I think now, to be honest, they're sick of reporters. But in those days, this was back in 2004, they weren't yet. And so the people there were very kind to me, very generous to me. And for those of you who don't know the story, Shishmaref, you can see, is a very tiny, very narrow island. And it's effectively just being eroded away. And the basics for this are that the sea ice used to come in the fall and encircle the island, and it was protected from the wave action of these fall and winter storms that they get in that part of the world. So it was like sort of like laying a tarp on a pool. But now the sea ice is coming in later. Some winters it has not come in at all. And so the island is getting ripped apart. And another factor here is that the ground there is permafrost. And it's thawing. So it's like taking a pile of frozen dirt and letting it thaw, and you'd expect that it would start to fall apart. So this shows you, this is a sort of typical after-storm scene. They had to move a lot of houses closer in or away from the coast, but as you saw from the previous picture, there's not many places to move them. So the island of Shishmaref is eventually going to be gone, and people are going to have to move. But they are actually still there. They're waiting for a federal appropriation to move. It's a very expensive proposition to move, and that's a whole other political problem. But we are up here, we are, as I said, off the Seward Peninsula. So we are above the Arctic Circle, right at about 66 degrees north, and right where the Bering Land Bridge was in the last ice age. And people have lived in Shishmaref seasonally, archaeological finds tell us, for hundreds of years. maybe thousands of years, and now pretty soon they're going to be gone. So it's a very poignant story, and it gave the global warming story a narrative, a human narrative, I should say. And I just sort of tried to follow the story from there. I made several trips back to the Arctic, back to Alaska, to Greenland. This is a research camp that I visited on top of the Greenland ice sheet. So here we are on top of over a mile of ice, basically. And the scientists up there were looking at how temperature change was affecting the Greenland ice sheet, and a lot of, virtually everything, all the ice that comes off Greenland, all the ice that's melting off Greenland, which is a very significant amount, goes into sea level rise, because that's ice that's up on land, right? So you melt that, and it goes into sea level rise. So my goal was to get people to visualize what was happening right now to real people in real places, and then to use these stories as a lever, or if you prefer, sort of a window, to get people to think about the future that we are in the process right now of creating. And I just want to take a very slight detour here, because since I embarked on this project, as I mentioned, about 10 or 12 years ago, another issue has come up, which I've really come to see as just as significant as global warming, if not more so. It's sometimes called global warming's equally evil twin. And this is ocean acidification. And this is a biggie, and unfortunately, it's even harder to narrate than climate change. And that partly has to do with ocean chemistry, which turns out to be more complicated just in terms of the basic science. And partly, I think, because we're land creatures and we really don't have any intuitive sense of life underwater. So I'm sure many of you know about ocean acidification, but I'm just going to give sort of a quick tour of that. When we pour CO2 into the air, a lot of it, roughly a third of it, ends up in the ocean. And this is just due to, basic sort of chemistry, the partial pressure of CO2 changing. Basically, the air and the water interact and they readjust until they hit a new equilibrium. So here are some of the basics. The oceans have absorbed roughly a third of the CO2 we've emitted since the start of the Industrial Revolution, and a lot of work has gone into quantifying those figures. This is about 150 billion metric tons. Every hour, the seas absorb another million metric tons of CO2. And the net result is that the acidity of the oceans has already increased by 30%. So, once again, there will not be a test on this afterwards, but for those who are chemically inclined, this is what the process looks like. When CO2 dissolves in water, it forms a weak acid, carbonic acid. We drink carbonic acid all the time in soda. It's why your mom told you not to drink soda before you go to bed, because it can destroy your tooth enamel. It's also what gives soda its zest, that sort of slightly sour taste, why we don't like to drink flat soda. But even a weak acid, if you add enough of it, it's going to affect the water chemistry. And so that's exactly what's happening. The pH of the surface waters of all of the oceans in the world is declining. And pH has a lot of knock-on effects. It affects a lot of different processes in the water, a lot of different properties of the water. But one of the key things that it does is it makes it harder or more energetically demanding for organisms that build shells and hard skeletons, external skeletons out of the mineral calcium carbonate. And this is a thought experiment you can do, or a real experiment if you want to. If you've ever been to, the Caribbean, and you brought home a piece of dead coral, that's just basically pure calcium carbonate. Or you could even just take a piece of oyster shell that you maybe throw in your garden or something. And if you put that in a bowl of vinegar, it's going to start to fizz and dissolve. And if you put it in a fresh bottle of seltzer and you cap that bottle of seltzer, it will not fizz, but it will also start to dissolve. And long before it's dissolving, it's becoming harder for that organism to make the calcium carbonate in the first place. So here are just a couple of examples of things that build shells out of, or tests. They're sometimes called calcium carbonate. Those are tiny little creatures called coccolithophores. They sometimes produce these huge balloons that turn huge parts of the ocean that's sort of milky white. They're extremely common organisms. They are calcifying organisms. Are very common, mollusks, mussels, clams are calcifying organisms. Sea urchins are calcifiers. They're wonderful. This is a kind of starfish that you find on the Great Barrier Reef, fantastic blue color. They're calcifiers. And of course, corals are calcifiers. So when you hear this idea that coral reefs are doomed, this is what people are talking about. Even if reefs could survive rising water temperatures, which is possible, debatable, but possible, they really just can't make it in an ocean that's acidifying. They just can't grow, and many, many experiments have shown this to be the case. This is a quote from a fairly recent paper in Science. Under these conditions, which are conditions that are just continuing on a business as usual track, by the middle of the century, under these conditions, reefs will become rapidly eroding rubble banks. And I'm just going to show you one more ocean acidification set of ocean acidification slides. This is a really interesting place off the island of Ischia, so we're in the Bay of Naples now. And it's a volcanic area, that's where Vesuvius is, and in the water you're getting these vents of CO2 coming up from the bottom, coming up from underground. And this has naturally, if you want to say, acidified the water. So it gives us sort of like a window into the future. So this is what the fauna looks like if you are away from the vents, right? So it's really colorful. You see there are all sorts of calcifiers here. There's a sea urchin there. That pink stuff is a coralline algae, which is a calcifier. I won't bore you with many, many calcifiers you can see in this picture. But you see it's a pretty vibrant ecosystem there. Now, you see those bubbles. Those are CO2. We're just a couple hundred years away. We are at pH 7.8. And it looks like a moonscape, right? There's really not much there. And the key thing to understand here is that pH 7.8 is what we will reach ocean-wide if we keep on our merry way till the end of this century. So these were a series of photos taken by a National Geographic photographer, named David Lichwager, who's a wonderful photographer, and I went in the water there too, and it was the most freezing experience I've ever had in my life. I went in the middle of January when the water's clear. So that was another one of my attempts to tell this story in a conventional journalistic way. Excuse me. This was a story that ran in National Geographic about a year ago. And I can't say that it had a lot of impact. And National Geographic hasn't asked me to do another story, so maybe that says it all. So I call my talk today, or in the Anthropocene. And the Anthropocene is a term that was coined by Paul Crescent, whom I mentioned earlier as one of the discoverers of ozone-depleting chemicals. He's a Dutchman who works in Germany. And it means, it doesn't really even have a correct pronunciation. People pronounce it all sorts of different ways. It means the era of man. Technically, we now live in the Holocene, which started about 12,000 years ago when the ice sheets of the most recent glaciation started to recede. And if you've been standing here in Boston, which would, of course, have been possible 12,000 years ago, you would have been standing on, or perhaps under, depending on how you want to look at it, a massive ice sheet, an ice sheet about a mile thick. So the Holocene began when those ice sheets started to melt. But there's a very serious move afoot to put us in a new geological age. Geologists are actually looking into this, whether we should formally designate a new age to acknowledge the fact that we, human beings, have become the driving force on the planet. We are now a force on a geological scale, the force, really, dwarfing forces like volcanism and plate tectonics, which have shaped the planet's history for all of Earth's history. And of all the ways we are changing the planet, warming it up. My